Alright, in this video I'll be talking to you about number theory, which sounds kind of complicated, but it's just some real basic topics such as prime numbers versus composite numbers. We'll discuss divisibility. We'll look at prime factorizations and how we can use those to find greatest common factors, or GCFs, and LCMs, which stands for least common multiples. So a lot of what we're doing is a foundation for what we'll do when we deal with fractions. All right, so let's get started. Let's talk about divisibility first. And you can see here we have the natural numbers, which are sometimes called the counting numbers, 1, 2, 3, 4, and so on. We have some language that we use when we talk about divisibility. We could say 30 is divisible by 3, or 3 is a divisor or factor of 30, or 3 divides into 30. It's probably worth mentioning the difference between divisors and factors. They're essentially the same. It's just when we're talking about division, we normally use the word divisor, and when we're talking about multiplication, we use the word factors. All right, so let's look at our divisibility rules. Most people know the rules for 2, 5, and 10. Let's go ahead and look at those as well as some others that are kind of nice. It's nice to know whether a number divides into some bigger number, and so these rules can be helpful. So certainly if you're an even number, you're divisible by 2. So any number ending in a 0, 2, 4, 6, or 8. The rule for 3 is kind of tricky, or not tricky, it's kind of cool. The sum of the digits is divisible by 3 here. Notice for 9, the sum of the digits is divisible by 9. And so for 3 and 9, you have that same basic rule. You add the digits. In the case of 3, if your sum is divisible by 3, then the original number is divisible by 3. So it's a nice way to know if a number is divisible by 3. The rule for 4 is if the last 2 digits are divisible by 4, then the whole number is. Of course, for 5, it just ends in a 0 or 5. It turns out that if a number is divisible by 2 and 3, it's also divisible by 6. I don't know how useful the rule for 8 is, because you're just checking to see if the last 3 digits are divisible by 8. Which is not necessarily easy, but you can use that. We talked about the rule for 9. It's just like the rule for 3. Of course, the rule for 10, it just ends in a 0. And finally, the rule for 12 is if the number is divisible by 3 and 4, then it's divisible by 12. All right, so let's go ahead and move on to the next page and practice. Oops, I forgot to write out I wanted to mention the whole numbers, which are the same as the natural numbers, except for they include 0. All right, let's move on. So in this problem, we have 4 numbers, and we're going to check to see if they're divisible by 2, 3, 4, 5, 6, 8, 9, 10, and 12. So let's look at 800. So certainly 800 is an even number, so it's divisible by 2. 8 plus 0 plus 0 is 8, and that's not divisible by 3. And so 800 is not divisible by 3. The last 2 digits are 0, and 0 is divided by any number, or divisible by any number, and so it is divisible by 4. Certainly 100 would be divisible by 4 as well as 800. Let's see, 5, it ends in 0, so yes, 5 is a factor. Now for 6, 2 and 3 don't both work, so 6 won't work. 8 is certainly a divisor of 800. 9 is not going to work because 3 didn't work. If a number is not divisible by 3, it won't be divisible by 9. Remember, the sum of the digits was 8. That's not divisible by 9. Certainly we're divisible by, so we said 8 and 10. And since we're not divisible by 3, 3 and 4 don't both work, so we're not divisible by 12. So it's just 2, 4, 5, 8, and 10. So I would encourage you to try numbers 2, 3, and 4, and then watch the video. All right, so on number 2, you should have gotten that 2 works, because notice it is an even number. 3 works, because 5 plus 3 is 8, plus 4 is 12, and 12 is divisible by 3, and so 534 is. Now the rule doesn't work for 9, because notice 12 is not divisible by 9, and in fact none of the other numbers work. Let's look at number 3. It's an even number, so certainly 2 works. If you add up the digits, 2 and 9 is 11, and 1 makes 12. 7 and 8 is 15, 12 and 15 is 27. Notice 27 would be divisible by 3 and 9. So I'm going to go ahead and put both of those down. And we also know that if 2 and 3 are divisors, then 6 will be a divisor. Whoops, I got ahead of myself there. And in fact, those are the only numbers that work. And let's see. On number 4, almost everything works. 2, 3, 4, 5, 6, 10, and 12. All right, let's look at prime factorizations next. First of all, our definition of a prime number is a natural number having exactly 2 factors, 1 and itself. For example, we know that 5 is prime because 1 times 5 is the only way to multiply 2 numbers and get 5. So the number 5 has just 2 factors, 1 and itself. So that's how it works with prime numbers. A composite number is a natural number having 3 or more factors, or in other words, more than 2. So on number 5 here it says, write the prime numbers that are less than 30. Well, let's go ahead and go through that. So it turns out 1 is not prime. It doesn't have 2 factors. It actually just has 1. 1 is the only factor of 1. So it's actually neither prime nor composite. 1 is a special case. So 2 is, let's see, so 2 is, actually 2 is the only even prime number. 2 times 1 is the only way to get 2. Whoops, what's going on here? There we go. So 2 works. Notice 3 times 1 is the only way to get 3. 4 doesn't work because 2 times 2 is 4. But 5 does. 6 doesn't work because 2 and 3 are factors of 6. But 7's prime, and then 11, 13. Notice at this point we're just looking at odd numbers. 15 is divisible by 3 and 5, so that's not going to be prime. 17 works, 19, 23, and 29. So these are our prime numbers less than 20. And honestly, we probably only need about the first 5 or 6 most of the time. All right, let's look at number 6. It says determine whether each number is prime or composite. So there's a nice easy way to do this. You can either tell just because you know your factors, or there is a nice systematic way you can do this, which I'll mention in a minute. So certainly 9 is not prime because 3 is a factor other than 9 and 1, and so it would be composite. If you check 31, it has no factors other than 1 and 31, so that would be prime. 78, notice 7 plus 8 is 15, and 15 is divisible by 3, so we know that 78 is, and so it is composite. 78, oh, and actually it's an even number, so let's see, I made it harder than it had to be there. How about on number or letter D here, 5001, 5 plus 0 plus 0 plus 1 is 6, 6 is divisible by 3, so the whole number is. And so that would be composite. We talked about 1. We said that's neither. With 73, if you run through all your prime... So basically, sometimes we think we have to check every number, but we actually just need to check the primes. And in fact, we can check the primes until that prime number squared is bigger than the number we're working with. So here we're working with 73. 11 squared is 121, and so we don't have to check anything bigger than 11. Notice 7 squared is 49, which is less than 73. So we have to check the prime numbers up to 13, and none of those are divisors of 73. And so 73 is prime. Now notice 117 is another one of our numbers that's divisible by 3. So, because 1 plus 1 plus 7 is 9. 9 is divisible by 3, so the whole number is. In fact, this number is also divisible by 9. So this is a composite number. All right, let's move on to the next slide. So the next thing I want to mention is the fundamental theorem of arithmetic. Sounds kind of complicated, but it's actually quite basic. Every composite number can be expressed as a product of prime numbers in exactly one way. So number 7, find the prime factorization of each number. All right, so, excuse me. First of all, there's more than one way to do this, but you'll always end up at the same place. And the main thing to remember is as you're breaking these numbers down into their factors, we're looking for prime factors. And so 54, when I think of 54, I think of 6 and 9 as factors. And neither of those are prime. Well, 6 can be written as 2 times 3, and those are both prime. So notice I'm going to circle those. And 9 is 3 times 3, and so those are both prime, and so we can write 54 as 2 times 3 to the third power. All right, so let's look at B next. 120, now I think of 120, I think of 10 times 12. Again, you could have used 2 and 60, and you'll still end up at the same place. So 10 can be factored into 2 times 5. Now sometimes people might write like 1 times 10. We don't break anything down using a 1 because 1's not a prime number. We're trying to use only primes. And so, but 2 and 5 would work, and those are both primes. 12 we can write as 3 times 4, and the 3 is prime, but the 4 is not. And we can break that down into 2 times 2. And so finally we can write 120 as 2 cubed times 3 times 5. Notice we try to write the prime numbers in order, and we also put in the exponents. We use exponents. All right, so you may want to try C and then watch the video. All right, so we're going to prime factor 234. So certainly this is an even number. We can write it as 2 times 117. And 2 is prime, and I'm looking at the 117 and I realize 1 plus 1 plus 7 is 9. This number is divisible by 3 as well as 9. So I'm going to divide it by 3. It turns out it's 3 times 39. And 3 is prime. And so now we can break 39 into 3 times 13, and those are both prime. And so our prime factorization here is 2 times 3 squared times 13. All right, I'm going to go ahead and stop here, and then I'll make another video on greatest common factors or divisors and least common multiples.